Okay, so now let's look at example 2 on page 3. The question says ABCD is a parallelogram. So on the side here, drawn ABCD, the arrows indicate that opposite sides are parallel to each other. So we've got a parallelogram. Part A says by drawing in the diagonal A to C, so A to C, that's the diagonal there, we want to show that the triangle ADC, so A to D, D to C, that triangle there, we want to show that triangle is congruent to CBA, which is the blue triangle there. So let's start off by writing down what we want to prove. So want to prove WTP. We want to prove that triangle ADC is congruent to CBA, just so we have a goal to work towards. Now, congruent, go back to page 1. What does congruent mean? Congruent means when the two shapes have the same shape and size. So there are 4 ways which we can test for congruence in triangles. Either we show that 3 sides the same, or 2 sides and 1 angle is the same, or 2 angles and 1 side the same, or a right angle, hypotenuse, and side is in common. We can't use RHS in this case because we don't have any right angles. In particular, I'm going to use AAS, angle, side, to prove congruence in the 2 triangles here. So, back up here, if my goal is to use AAS, I'm trying to show that one side is in common. Is there one side which is in common that has the same length? Well, is there any side which is overlapping with the blue triangle and the pink triangle? Well, yes, there is. The diagonal AC is in common. So AC is a common side. So we know that one side is of the same measurement. Next, I'm going to show that 2 angles are the same. So let's consider angle DCA. So angle DCA is this one here, the red angle. We want to show that it's the same angle as another angle in the blue triangle. Well, if you think about it, this side AB is parallel to DC. So using the alternate angle rule, the Z rule, this angle BAC is also the same measurement, same angle size as angle DCA. So we can write that down. So angle DAC is equal, whoops, wrong color pen, is equal to angle, right, now we have to match up the vertices. Okay, let's think about it. DCA, right, so C, so if you redraw the triangles, D matches up to B, right? So this angle A matches up to angle C. So if D matches up to B, so it becomes angle B. The C and the A match up, so we have BAC. Okay, so that's one angle there done. Let's look at another angle. Oh, we forgot to justify why the angle is the same. So we draw in the alternate angle symbol, or you want to write the word alternate angles. Now we need to show that another angle is the same. So let's consider angle DAC. So DAC, so that's this blue angle here. Again, because we've got parallel sides, by the alternate angle rule, this is the same angle. So again, D matches up to B, A matches up to C, and there we go. So angle DAC is the same as BCA. And why? Because of the alternate angle rule, either write the word or draw the symbol. So therefore, we can justify that triangle ADC is congruent to triangle CBA. Why? Because of a angle side. So that's part A done. Part B says, use these triangles to prove that angle ADC, so ADC is this one, is equal to ABC, which is that one there. So that's part 1 of part B. So want to prove that angle ADC is the same as angle ABC. Now, if we're considering back our 2 triangles, so it's the blue one and the pink one, we proved in part A that the 2 triangles are congruent. Now we said that congruent shapes have the same size and shape. So what this means, all the angles are the same as well. Now because the blue triangle and the pink triangles are congruent, then immediately the 2 angles in the triangles, the corresponding angles, must be the same. So we can write, so since triangle ADC is congruent to triangle CBA from part A, we know that angle ADC must equal to angle ABC. That's just a given because we proved congruence. Now, part 2 of part B says we want to prove that angle DAB is the same as BCD. Alright, so let's go back to our diagram. Let me rub off some of this annotation. Okay, so DAB, that's this angle here. We want to show that's the same as this angle BCD. Okay, well, let's first break apart angle DAB. Okay, so angle DAB can be broken apart into angle DAC and angle BAC. Can you see that? So DAC is this red part, and BAC is this black angle there. So if you add those 2 together, you get DAB, which was the blue part. Okay, so how does that help us? Well, let's also break apart angle BCD. So angle BCD can be broken apart into the angles within the 2 triangles, which is a BCA and angle DCA by the same logic. If you look at the picture, half the angle plus half the angle gives you the full angle. But what do we know? But we know that angle DAC is the same as the angle BCA. Why? Well, what is DAC? DAC is this angle here. Right, DAC, that is the same as BCA, that one there, because of the alternate angle rule, since the Z rule, alternate angles. And we also know that angle DCA is the same as BAC. So let's have a look back in the diagram. I'll rub that off. Was it angle DCA, this angle here, that is by the Z rule the same as the angle BAC, again because of the alternate angle rule. And because they're the same, we can say that therefore angle DAB, which we broke down to angle DAC and angle BAC to become angle BCA and angle DCA, because we saw down here that they're the same angles, which means if we look at BCA and DCA, which was exactly angle BCD, so which is the same as angle BCD. So therefore we can conclude that angle ADC is the same as angle ABC, and we also shown that angle DAB is the same as angle BCD. So part C is asking, what special property of the parallelogram does this prove? Well, if you look at where angle ADC and ABC are, so ADC, this one and that one, they're the same, and we show that DAB, this angle, and that angle is the same. So we have just proved the property that opposite angles of a parallelogram are equal. So back on page 1, That was the first dot point where both pairs of opposite angles are the same in magnitude. So we can write that down. So part C, it's saying the property proved is that the opposite angles of a parallelogram are equal. Okay, so part D we're up to. By now drawing the diagonal B to D, so we've got this new diagonal in, we want to show that triangle CDE, so that, let me highlight it, so pink CDE, pink triangle is congruent to ABE. So you want to prove that the blue and the pink triangle are congruent to each other. Again, we have 4 ways to prove congruency. I am going to use AAS. Okay, so if we can find a common side and prove 2 angles are the same, then we are good to go and ready, and we can show that the 2 triangles are congruent to each other. Okay, so how do we do this? Well, we want to prove that triangle CDE is congruent to triangle ABE. The first observation I can make is angle DCE is the same as angle BAE. Let's have a look at why. So angle DCE is this red angle there. I'm saying it's the same as BAE. Make sure you match up the vertices, the corresponding vertices. Why? Because again, the sides are parallel and we just applied the Z rule, the alternate angle rule. So that is true because of alternate angles. I can also make the claim that angle CDE is the same as angle ABE. So let's have a look at where it is in the diagram. So angle CDE, this blue angle, we're saying it's the same as this angle AB. Again, because of parallel sides, we can say that's true because of the alternate angle rule. Now, lastly, we need to find a common side. I make the claim that AB is the same as CD. So think about it. AB is the same as CD. Why? Because back in part A, we already proved that triangle ADC is congruent to ABC. Right? So because triangles are congruent, then the sides must be the same length as well. So we're using part A to show that part D triangles are congruent. So this is true. Why? Since triangle ADC is congruent to triangle CBA, that's from part A. So because we have angle side, therefore triangle CDE is congruent to triangle ABE. Why? Because of angle side. Okay, so that's part D done. Part E says use these triangles to prove that AE equals CE and DE equals BE. Okay, so where is CE? CE is here. So E is the point where the 2 lines intersect, the 2 diagonals intersect. So we want to show that CE and AE are the same. And then we want to show that DE and BE are the same. So it's actually trying to show that the diagonals are cut in half, right? So why is this true? So we know that A to E is the same as C to E. Well, because we proved that the 2 triangles, which was the blue triangle and the pink triangle, we proved in part D that these 2 triangles are congruent. Remember, congruent triangles have the same shape and size, meaning the side lengths are the same as well. So A to E is corresponding to C to E. And so that is why these two sides are the same. And the same can be said of B to E and D to E, because the green and the pink triangle, the blue and the pink triangle, we proved in part D, were congruent. Congruent means same side length, and so these two sides are the same. So I'm going to write this over the next page because I don't have enough space. So just over here, part E, since the triangle CDE is congruent to triangle ABE from part D, we know that AE must be the same as CE, just matching up the vertices, and DE must be the same as BE, because congruence means same shape and, more importantly, size. So the lengths are the same and the angles are the same. So part F is saying, what special property of the parallelogram did we prove? As I mentioned before, the diagonals, if the same length from DE to BE, it means that we cut the diagonal in half for both the long diagonal and the shorter diagonal. So the special property that we proved is that the diagonals of a parallelogram bisect each other, because remember, the word bisect means to cut in half. So the property proved is that the diagonals of a parallelogram, they bisect because they cut each other in half, each other. And that was the third dot point that we proved for a parallelogram. And the second dot point, that opposite sides are equal again, can be easily shown because we proved already that the triangles are congruent to each other, the blue and the pink. So example 2 is proving properties relating to a parallelogram.